Everyone, welcome to Technically You, the podcast where we break down complex tech into bite-sized brilliance. I'm your host, and today we're diving into something every network engineer should understand: link aggregation, also known as LAG.
Yes, and if you're in IT, networking, or just obsessed with improving your bandwidth and reducing downtime, LAG is a game changer. Let's get into what it is, how it works, and why it's such a big deal in today's high-demand environments.
So what is link aggregation, LAG? Well, link aggregation, let's simplify this. It's basically combining multiple physical network links into one logical link. Think of it as turning multiple roads into a super highway.
Exactly. Instead of relying on a single Ethernet connection between devices like switches, routers, or servers, you bundle them. That bundle acts as a single, higher bandwidth pipe.
It's also known as EtherChannel in Cisco land, port channel, or LACP, which stands for Link Aggregation Control Protocol.
And LACP is the IEEE 802.3 AD standard that helps automatically configure and manage those aggregated links.
Okay, let's talk about benefits. First up, increased bandwidth.
Right, if you combine 4.1 Gbps links, you effectively create a 4 Gbp logical pipe, perfect for environments with heavy traffic like data centers, media servers, or backup systems.
Second, redundancy. If one link fails, the traffic automatically shifts to the remaining links. No more relying on a single point of failure.
Also, load balancing. Traffic can be spread across all active links to optimize performance.
Now, let's talk tech. How does LAG actually work under the hood?
Each link in the aggregation group is assigned a role. Traffic is distributed using load balancing algorithms, commonly based on IP addresses, MAC addresses, or TCP or UDP ports.
And if LACP is enabled, both devices negotiate and agree on which ports to aggregate and how.
Without LACP, it's called static link aggregation. It still works, but without the smart negotiation features.
All right, let's talk about configuration and requirements. To implement LAG, you'll need switches or routers that support LACP or static aggregation.
You'll also want identical port speeds, duplex settings, and VLAN configurations on all aggregated links. Some systems don't tolerate mismatches.
And it's best practice to use contiguous ports for easier cabling and management.
Some folks ask, why not just connect two switches with multiple cables and let Spanning Tree Protocol, STP, sort it out?
Great question. STP blocks redundant links to avoid loops, but it wastes potential bandwidth. LAG uses all available links simultaneously.
Exactly. With STP, you get redundancy but no bandwidth boost. With LAG, you get both.
So where do we see LAG in action? Pretty much anywhere from enterprise backbones and server-to-NorWeb connections to storage networks.
Even some high-end home networking gear supports it now, especially in NAS systems or high-performance routers.
Okay, here are a couple of pitfalls with LAG. Mismatch settings are a big cause of LAG failure. Always double-check your configurations.
Also, watch out for asymmetric traffic, where one link gets overloaded while others are underutilized. Some load balancing algorithms aren't perfect.
Lastly, remember to monitor the flow of traffic. Using SNMP, NetFlow, or your NMS can help you keep tabs on how your LAG is performing. So what's next for link aggregation?
As networks scale, LAG is evolving. We're seeing more virtual link aggregation across switches with multi-chassis LAG and VPCs in data centers.
And with SDN, software-defined networking, LAG is becoming smarter, more dynamic, and integrated with intent-based networking.
Okay, let's wrap this session up with a final thought. LAG might not be flashy, but it's one of the best tools for boosting performance and reliability without spending a ton on bigger pipes.
Thanks for joining us today. Be sure to subscribe to Technical U for more deep dives into the tech shaping our world. So, as always, stay informed and stay curious.